Hello everyone, welcome to this second session on the magnetostatics. So in previous session we have discussed about the basics, the definitions, and we have also discussed about the permissions given by the mediums. So permissions, like in magnetic field, it is related to mu. This is like a virtual visa. We have to take visa to travel to different countries. We have to follow their permission levels, and according to that we have to get the access. So it is like virtual visa. Then we have seen the magnet, north pole, south pole. It will always be in two poles. We cannot separate them. We cannot make a single north pole or single south pole. This is a wave traveling in some x direction. It will have two components. Say this is electric field component, and say this is magnetic field component. Now we will discuss few more interesting facts about the production of magnetic field. Now the direction of magnetic field. What is magnetic field or electric field? They are not like charges or the actual current which flows in the form of electrons. They are just force lines. Like we can see the magnet, but we cannot see the force lines across the magnet. We cannot even touch magnet and feel that there are some force lines, but we can observe their force. If we bring small spoon or some iron material near this or small needle, we can see the effect of attraction. We can experience these force lines, but we cannot see them. They are not like charges or any solid material. They are like hidden software. So, but their effect is visible. Similarly, electric field, E, and magnetic field, these are some effects. Magnetic field particularly is created by the charges, the moving charges. So here we will consider one toy example. In this diagram we can see there is a conductor, and the red balls we are representing as the moving charges. Magnetic field cannot be produced by the static charges. Charges should be in motion, and once these charges are flowing up, say current direction is towards up, then the direction of magnetic field will be the direction of the curl of the finger. Curl means it's a circulation. So curl is also useful parameter in Del operator, that also we will discuss. Curl is a rotating force, like a twister. You might have seen the twisters of air or water like this shape in movies or television. These twisters have the force of curl. Similarly, these force lines will be created in air. So this force pattern will be different in the medium, like they will have the curl or they will have divergence. So when current is flowing inside a conductor, by default it will create a magnetic field, and that field will be calculated by right hand thumb rule. So what we have to do, just we have to consider the right hand, and the thumb will be the direction of current, and the direction of finger curl, that means in which direction fingers are turning, that will be the direction of the magnetic field. So this rotating field around this conductor is anti-clockwise in direction if this current is going up. So if current is going down, just we have to consider the down thumb. So down thumb, the curl will be in clockwise direction. So like this we have to remember the direction of magnetic field. Then this is also on another diagram. Here we can see, now here B and H, both of them we will relate interchange with interchanging concept. So in this toy example, we can see the current is going down. So when current is going down, the direction of magnetic field is clockwise. So either we can write H or we can write B, that doesn't matter. So B and H both are related to magnetic field. Both of them are given as with relation, say B is equal to mu H, where mu is equal to mu naught mu R. If mu R is 1, if it is a free space, then we can write it as mu naught, where mu naught is 4 pi into 10 to the power minus 7 henries per meter. So we have to remember this. Now one more parameter we will compare it with the Gauss law. Now D and B, both of them are densities, right? One is electric field, electric flux density, one is magnetic flux densities. So electric flux density, we can say who is creating electric flux, some charges, or electric flux, say we will represent it by psi, and it will have some surface area, say S. Now if we consider d bar due to small differential surface, and in that small differential surface there will be small differential flux. So from here what we can say, d phi will be equal to d bar dot ds bar, and then from here what we can say, full psi. How we will calculate full psi? Will be equal to, if we want to remove derivative this side, another side we have to take integration. So this side we can write integration of d bar dot ds bar, right? Now similarly, what is B? B is also magnetic flux density. So now here we are writing psi, here also we can write psi. For just for change, say if in some book we write d phi. So d phi is the cause, the flux is cause of flux density. Again if we consider ds, so what we can write from here, d phi or d psi will be equal to what? This will go to left side, it will be b dot ds. These are vectors. This surface, differential surface, is also a vector. So here what we can write, d phi is equal to b bar dot ds bar. So if we want to calculate the total flux, what it will be? This side we have to take integration. So it will be integral of, b is also a vector, so we can write vector. So it will become b bar dot ds bar. Is it clear? Now what is this thing? In more detail we will discuss. Here we have both electric and magnetic concepts. Now what is this flux crossing through some surface meaning? Suppose I have a surface, plane. Surface means we will consider a simple plane. It may be a square having two dimensions. It may be circle, triangle, or any random shape. Two dimensions only. So on this total surface, these are the total surfaces. What we do for mathematical purpose, we take small differential surface as sample. Here we will take small differential surface for our study purpose. Here we will take small differential surface. Here small differential surface. Here we can take small differential surface. Now these flux lines are like the invisible force line. So let us consider this force line is coming like this, like arrow, say D, or if it is current carrying, say it is B. So how much in this total area, what is enclosed? Some flux or charge is enclosed, right? So what will be the enclosed value of flux in small differential area? d phi. So from here what we can say, this d phi is nothing but this product of B dot ds. Now why we are taking ds? Now when we say, so what I will get, total phi is equal to say integral of B bar dot ds bar. ds bar means surface. Surface integral will be single, double or triple? Yes. So for that we will see a small thing. Say what we can have, we can have one single point charge Q. So we can have number of charges placed one after one. It will make a line charge. So it may be given by some symbol. In our book we use rho L. In some other book it may be some other symbol like rho or something. Okay. Now this line, so many lines connected, it will become a surface. In that there will be surface distributed equally, surface charge distribution. Now there can be a volume. Volume can be a cube or any other shape or a sphere. Sphere, a football is also a volume. So here we will have rho v, here also we will have rho v. Now single point charge is single point charge. One line is a single dimensional line. So if I want to write E bar dot dl bar, if I take its integration, it will be single integration, because what? Only one direction it can go, x or y, right? Now if I take surface, normally in the case of say B bar dot ds bar or D bar dot ds bar, in that case if I take differential surface, say D bar dot ds bar, Gauss law, how many dimensions will be here? Two dimensional, either x, y or y, z or something else. So how many integration? It will be double integration. Double integration means what? This ds will have some value. Suppose this is 0 and this is 1 and this point is also 1. That means it is going 1 meter on x axis, it is going 1 meter on y axis. So how we write this same expression? Double integration means what? This ds will be product of now dx dy. What is this differential surface? This is nothing but small differential x, small differential y combinedly making one differential surface. So what we can write here? Say d bar into dx dy. What are the limits for x and y? We write in the integration. For x, so x equal to, where it is starting? 0. Where it is going? 1. X equal to 0 to x equal to 1. This side, how much it is going? Say my surface is going starting at, now y is starting at 0. Where it is going? Y is equal to 1. Now this is double integration because two dimensional. Now what about a volume? How many dimensions? 3 dimensions. So x, y and z. So if I want to write a formula for a volume, so psi will be equal to say what is this? B is equal to density equal to the creator of density, say we will consider small area. Now this area, if we consider sphere, so what will be the area of sphere? 4 pi r square we can write. Or if it is a cube, then what we can write? Say d. From here what we can write? D phi is equal to b into d a. If I want to write phi equal to, what I will write here? Which integration? Double or triple? It is area for a volume. So say we will write dv for simplicity. So for dv how many integration? 3 integration, triple. So here B bar dot, now this dV may be dx into dy into dz. So here x equal to some value starting, x equal to ending value, like this we will put the limits. So this is psi is equal to, or phi is equal to B bar dot ds bar or B bar dot dV bar. So let us move to next. So next we will start BIOT Savarts law. What BIOT Savarts law states, it is like it is also called as Ampere's law of current element. So it states that same thing, that current carrying conductor creates the magnetic field. Now in electric field we consider Coulomb's law. We will compare it with electric field. In electric field we consider Coulomb's law as the basic law. It is treated as the basic starting law, and we consider Gauss law as a case of Coulomb's law. In magnetic field what we do? Magnetic field we consider BIOT Savarts law as the basis or basic laws like Coulomb's in electric field, and Ampere's circular law as a case of a further extension of BIOT Savarts law. So first let us discuss the BIOT Savarts law, and few more things before proceeding. We may have dl, we may have ds, or we may have dv. These position vectors we consider as vectors, dl bar, ds bar or dv bar. That means what? It will have one, this length will have some magnitude, say 5 meter, 10 meter something. So it will have combination of one magnitude, and it may have some direction, x direction, y direction or z direction. So this we consider like this. So now let us study BIOT Savarts law. It's very simple law. So what BIOT stated that, here this diagram we will consider. Here we have one current carrying conductor. The shape and scale is not to be considered, it's just a toy example for understanding the setup. So here current is flowing across this conductor, and we are considering one test charge. And what we have to do, we have to calculate the magnetic field on this test charge. That is nothing but the formula for, that is what BIOT Savarts law gives us. Now what is this assembly? If you want to compare this current carrying conductor, you can compare with one mobile antenna. So this is mobile antenna. Okay. Now there will be different point charges. Point is considered as a single point. These are all point charges, very tiny objects. For understanding purpose we are showing them as some big sphere, because if we extend this point charge in all directions, its shape will be like a sphere. Everywhere these point charges are present. Now let us consider everywhere these point charges are nothing but different mobile phones. So each point charge will consider as mobile phone. So everywhere their mobile phones are there, right? Now this antenna will have some effect, some strength on all these antenna, all these mobile phones. So how much effect of this antenna is there on this mobile, and how much is there on this mobile, or how much is there on that mobile? How much is his effect on that? That is nothing but the strength of our signal. And what is our signal strength? Magnetic field and electric field. What you say? What may be the strength on this mobile? Will it be more or less compared to this mobile? It will be more because he is near. So distance is main parameter. As distance increases, the effect of strength decreases. Right? So what we are doing in electric field also we do the same thing. In magnetic field chapter also we are doing the same thing. What is that same thing? We consider a source, and this source in this case is our current carrying conductor, and we find out its effect of say magnetic field on different point charges. So it will be inversely proportional to the distance and directly proportional to the related cause who is creating it, either this strength, who is generating this strength. In the case of current conductor, first thing, current is creating it. So directly proportional. You increase the current, get more effect on the surrounding region. Here we are considering one space charge. Like that there will be so many charges present in the space. Everywhere its effect will be different. Directly proportional. So what BIOT Savarts say? It will be directly proportional to the current. And the length of the conductor. You increase the length, you make a bigger antenna. You get more range. You increase the length, you get the more strength. So what he is saying, very simple concept. Suppose B or H we consider. So wherever I use H, you consider it as B only. So say I am writing H. Okay, and I am considering a small differential length dl. In that small differential length dl, current I is flowing. So what BIOT Savarts said, this effect on the test charges is directly proportional to the current and the length of the conductor, because they are directly affecting the signal, and there may be some different angles of these point charges in space. Now this mobile phone at different location with different angles, this mobile phone in space at different position, different angles. So that sine angle with horizontal he asked us to consider. So he said H is directly proportional to ideal sine theta. Then what he said? This H or B is inversely proportional to the distance. As you go away from the source, the signal strength will decrease. So what is his another statement? H is inversely proportional to the square distance between them. Now just we have to club these two. So what will be H? So H, so says we are considering DL, so here we will have DH only. So say DH, we can say directly proportional to I DL sine theta divided by R square. Now to remove this proportionality sign, we have to add some constant. So say we'll get DH is equal to IDL sine theta by R square. Right? Now we will compare this one with the electric field formula. What is electric field formula? For say single point charge, say it was E is equal to Q by, what is it? 4 pi epsilon naught R square. E was direct cause of charge, because we have seen a single static charge can also act like the sun. He is sending out positive charge, electric field outside. Inversely proportional to R square, that is also inversely proportional to R square. But that is directly related to current, because it is created by the moving charges. Current is nothing but moving charges. There is one difference. Second, here constant of proportionality is 1 upon 4 pi epsilon naught. There K will consider as 1 upon 4. Say K will be equal to here this. Here we have to add this constant of proportionality K. This K here is given upon by K by 1 by 4 pi. because this is magnetic field, epsilon we don't consider. In free space normally we don't have magnetic iron and all, so we are not taking mu there. So what we will keep? We'll keep this 1 upon 4 pi here. So what will be the formula for dH? dH will be equal to I dl sine theta divided by 4 pi r square, right? So from here what we can say, H will be equal to how? This is differential H. How we will find out to overall H? What we should do with right hand side? If I want to remove this d, only H I have to write. Right side what I have to do? I have to take integration, right? Now further we will simplify this expression. Now this dH we have written in scalar form. We are not writing H bar. If we write H bar, what we have to add? We have to add the AR cap, that is the direction. So this half part is magnitude and AR cap is direction, the only direction. So now further we will simplify it. Say we got one expression. What is our expression? D say dH bar. Now this is vector I dl sine theta by 4 pi r square into AR cap. Now for simplification we will use one relation. That relation says that, say here we have cross product actually. If we have to take A cross P, then we can write it as AB sine theta. Now in this our expression we will consider one term as A, one term as B. So let us consider ideal. Let us consider ideal as A and AR cap as B. Sin theta is there. So A cross B is written as ideal sin theta. So what we can write? We can write it in the form as, so DH bar will be equal to ideal A cross, who is B? AR cap. So we will write AR cap here. So say this is not here. So ideal cross AR cap. Denominator we are not making any change, so we can write it as 4 pi r square. Now further for some examples we can simplify it. For that let us discuss about AR cap in brief. Now in next session let us explore this expression in more detail, and then we will continue with the application of BIOT Savarts law. Till then, have a good day. Thank you.